All right, we're working on the second homework, which is algebraic limits. We talked a lot about in class about a lot of theoretical stuff, but here's where we're actually going to be doing a lot of the mathematics here, although we will start here with a theoretical question in some sense. For what values of a does the limit as x goes to a of r of x equals r of a if r is a rational function? So remember that a rational function is the ratio of two polynomials. So there will be one polynomial over another. And the hope is that we're good and can just plug in the a as long as a doesn't make this denominator 0, because that would ruin everything. So we just want a to be in the domain of the rational function. Let's see what the answer choices say. Those values of a for which the numerator of the function is not 0. Those values of a for which the denominator of the function r is not 0. Okay. Those values of a for which the denominator of the function is 0. Those values of a for which the numerator of the function r is 0. So this is clearly a question about the denominator, as we just said. So it says, for what values is the limit actually equal to r of a? It's those values of a for which the denominator is not 0 are the ones that we're looking for. It's B. Explain why the limit as x goes to -5 of this is the same as this. Well, it's just factoring, right? So if you factor this thing for values of x that are near -5 but not actually equal to -5, then the factors of 10 that add up to 7, 5 and 2, and then we're going to cancel. So this is the limit as x tends to -5 of x plus 2. Let's see what the answer choices say. Since each limit approaches -5, it follows the limits are equal. No. The limits x squared plus 7x plus 10 over x plus 5 and limit as x goes to -5 of x plus 2 equal the same number when evaluating using direct substitution. I did not plug the -5 directly in. The numerator of the expression simplifies to x plus 2 for all x. No, that's not true for all x. I can't cancel this for every x, but I can cancel it when x is not -5. The answer is D. When you evaluate the limit, of course, then you're just going to plug -5 into, for x, you get -3. Factor, cancel, plug in the -5. That tells you what the limit is. Doing some algebra stuff with the limits. The limit as x goes to 5 of f of x is 5. The limit as x goes to 5 of g of x is 7. And the limit as x goes to 5 of h of x is 6. Compute the following limit. Well, if as x goes to 5, if f goes to 5 as well, g goes to 7, and h goes to 6, if there's any justice, this should be 5 over 1, which is 5. And it is. What do we use here? We used difference, this subtraction sign here. We use quotient, which means we were dividing. Assume that the limit as x goes to 4 of f of x is 7, and the limit as x goes to 4 of g of x is 8. Compute the following limit and state the limit laws and justify the computation. All right, so f is going to 7. G is going to 8. If there's any justice, this thing should be going to the cube root of 7 times 8 plus 8. Cube root 56 plus 8, 64. Cube root of 64 is 4. All right, so you're just plugging in the values. What are we using there? We're using a root rule. We're multiplying product and then we're going to add the sum, right? Root, product, sum. Now that we have all these nice algebra rules, we are going to roll through some of these. Now that we're using this, we can just plug in the number. The limit here is 4 times 1 minus 6. 4 minus 6 equals -2. We'll plug in -1 into this. 2 times -1 cubed minus 2 times -1 squared plus 4 times -1 plus 5. -2 minus 2 minus 4 plus 5. -8 plus 5, -3. The limit exists and it's -3. Plugging in the 4, 4 times 4 squared plus 3 times 4 minus 1 over 5 times 4 minus 5. Now again, let's be clear. If this was plugging in 1, we would do something different because it would make the denominator 0. But we're just plugging in 4. This is going to be 64 plus 12 minus 1 over 20 minus 5, 15. Let's hope this comes out nice. Ooh, that's a 75 over 15. A beautiful 3. Just straight up plug in the number. All these rules we've been building up to, again, just plug in the -9. 18 minus -9, all raised to the 4/3. That's 27 to the 4/3, and we'll break down what this fraction means. The 4/3 power means that we're going to take the cube root and then raise it to the 4th. So I'm going to take this as 27 to the 1/3 to the 4th. Well, what does it mean to raise something to the 1/3 power? That means I'm going to raise it. This is going to turn into the number you need to multiply 3 times to get 27. That number is 3. 3 to the 4th is 81. All right, or straight up put that in the calculator, putting in 27 raised to the 4 divided by 3. It'll tell you that that is 81. When I plug in the 4, if you plug in the 4, you're going to get 0 over 0, which means that you need to factor. So plugging in the 0 is not going to do anything, so this is going to be equal to the limit as x tends to 4. Factors of -20 that are 1 apart, x minus 4, x plus 5, all over x minus 4. The x minus 4's cancel. This is equal to the limit as x tends to 4 of x plus 5, and we now know that we're just straight up plugging in the number. This is 4 plus 5. This is 9. So this is equal to what so the answer they want here is that it's x plus 5, and then evaluating it, plugging in the 4, it gives you 9. Here we got some work to do. Again, we're going to plug in the number, and again, if you plug in the number, you can plug in the number, you're going to get 0 over 0 again. So this one, we're going to reduce the fraction. Okay, so this is called a complex fraction. I'm going to add a page here to do this one on its own. All right, so you have one fraction inside of another, you have a couple fractions inside of another fraction. The thing we want to do is find the common denominator, right? So the common denominator is 6 times 6 plus h. And if you do that, you're just cross multiplying then. So then it's 6 times 5, which is 30, minus 5 times 6 plus h. This is going to be equal to the limit as h tends to 0 of 30 minus 30 minus 5h all over 6 times 6 plus h all over h. This is equal to the limit as h tends to 0. So all I did here was distribute the 5. 5 times 6, 5 times h, and it's a negative 5. The 30s cancel. I'm left with a negative 5h over 6 times 6 plus h, all divided by h. What happens is that I have this h is being divided by that h. They cancel. So this is equal to the limit as h tends to 0 of negative 5 over 6 times 6 plus h. And now we notice that our issue with plugging in 0 is now gone. So now we can plug in 0, and this is going to be negative 5 over 6 times 6 plus 0, negative 5 over 36. So the answer they want here, if we go back here, is probably going to be something involving this. So negative 5, or it should be this, negative 5 over 6 times 6 plus h, canceling out the h's. Negative 5 over 6 times 6 plus h. And then plugging in the h equals 0, negative 5 over 6 times 6. Same thing here. We'll use a method called the conjugate. If you plug in 196 here, again, you'll get 0 over 0. And so that means that we will do some algebra. And the algebra here is called the conjugate. So we're going to multiply the numerator by the conjugate of the square root of x minus 14, which is the square root of x plus 14. This is the limit as x tends to 196 of the square root of x minus 14 over x minus 196. And then what we're going to do is multiply the numerator and denominator by the square root of x plus 14 over the square root of x plus 14. And the reason why we're doing that is that when we do that, nice things will happen in terms of canceling. This is equal to the limit as x tends to 196. Now when you do the square root of x minus 14 times the square root of x plus 14, the square root of x times the square root of x is a very nice x. The square root of x times 14 is plus 14, the square root of x, minus 14 times the square root of x, and then negative 14 times positive 14 is minus 196, all over x minus 196 times the square root of x plus 14, just the denominators next to each other. Well, these cancel. This leaves us with the limit as x tends to 196 of x minus 196 over x minus 196. Sounds like a canceling is about to happen over the square root of x plus 14. And all of that was just to make sure that this cancels with this. And so we're left with the limit as x tends to 196 of 1 over the square root of x plus 14. And now we'll plug in the 196. This is equal to the 1 over the square root of 196 plus 14. The square root of 196 is 14. 1 over 14 plus 14. The answer is 1 over 28. So all of that conjugate stuff and multiplying by it was to get nice canceling happening and turning it into something in which we could just plug in the number. So this turned into 1 over the square root of x plus 14. And then when you plugged in, you got 1 over 28. Consider the function f of x equal to f of x over g of x. You know that g of a is 0. Does f necessarily have a vertical asymptote at x equals a? Not necessarily, right? So suppose I had x minus 1 times x plus 1 over x minus 1, right? So, and we want a to be 1, right? Again, as we said in class, if you can cancel the factors, you don't necessarily have a vertical asymptote, you just have a hole. Let's see what the choices say. No, for example, they give us examples. X squared minus 4 and so x squared minus 4 and x minus 2, that factors is x minus 2, x plus 2. And here's a case where you cancel. So this one's looking right. Then the function f does not have a vertical asymptote at x equals 2, even though g of 2 is equal to 0. Ooh, I really like that one. So will we know the answer is no? What's the other no? No, for example, f of x equals that, g of x equals that, and a equals -1. No, this is the wrong. If this was the numerator and this was the denominator, then we might be good. The answer is A. Again, remembering that holes occur, you don't have to have a vertical asymptote if the denominator is 0, if you can cancel out the factor that makes the denominator 0. Here we're gonna be talking about limits at infinity. So the question is, what's the limit as x goes to -1, right? And so the question is, you're on the graph, and for the first time, x is going to -1. Here is -1 here, and let's see what happens on the left and on the right. So on the left, getting to -1, ooh, it looks like you're going farther and farther down forever. We got a name for that. Negative infinity. On the right, it looks like the closer you get to -1, you go farther and farther down. That also looks like it's negative infinity. That's our term for what happens when you have a vertical asymptote, and on both sides of that asymptote, the function just continues to go down, 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 down to minus infinity. We'll look at some other graphs. This one's expansive. Let's get it. All right, the graph of the function below has vertical asymptotes at x equals 3. Here it is here, and x equals 5. Find the following limits. Use infinity or negative infinity when appropriate. The limit as x goes to 3 from the left. Here's to 3. Here's 3. From the left, that thing's rolling down to minus infinity. 3 from the left. Negative infinity. 3 from the right. Oh, from the right of 3, you're way up here. Positive infinity. The limit from the left is negative infinity. The limit from the right is positive infinity. This limit does not exist. So for C, we would say the limit does not exist and is neither positive or negative infinity. Let's check out 5. The limit from the left of the graph for 5 on the left, rolling all the way up to infinity. On the right, coming from the right, oh, that's also going to infinity. In that case, we would say that the limit on either side is infinity. Roll through another one. Got some issues at -2 and 4. On the left side of -2, rolling up to infinity. On the right side, on the right side of -2, that thing's going all the way down. Let's see if I get the full picture. Yep. To minus infinity. So that means that there is no limit. because you didn't get the same thing on both sides. Limit as x goes to 4 on the left. Ooh, 4 on the left. I'll put it in green. 4 on the left looks like it's doing that. And 4 on the right looks like it's doing that. Both sides going to minus infinity. All three of these, minus infinity, negative infinity, negative infinity. Number 16. Similarly, I'm going to leave 16 to you. No, let's do it. All right. Limit as x goes to 4, negative 4 from the left. Negative 4 from the left, minus infinity. Negative 4 from the right, negative infinity. The limit, negative infinity. 5 from the left, 5 from the left, all the way up there, positive infinity. From the right, negative infinity. Limit does not exist. How many more of these are we rolling with? Oh, this one's fun. Sketch a possible graph of a function f together with vertical asymptotes that satisfy all the conditions. We'll just do some translating here. F of 2 is 0. It means it goes to the point 2, 0. F of 3 is undefined. That means there should be a whole or a vertical asymptote at 3. The limit is x goes to 4 if f of x is 1. Okay. So that means at 4, around 4, the function should be 1 foot above the x-axis. The limit as x goes to 1 from the right is negative infinity. This means that 1 is a vertical asymptote. So there should be a vertical line near 1, at 1. Okay, great. Oh, the limit as x goes to 3 of f of x is infinity. That means that 3 is also a vertical asymptote. Oh, same thing's happening at 5 on the left. So that means that 5 is a vertical asymptote. So we should be seeing 3 vertical asymptotes. Let's take a look here. At 1, at 3, and at negative 5, and it should hit the x-axis at 2. At 2, it hits the x-axis. All right, so they all seem to hit the x-axis at 2. Great. The limit from the right of f of x on 1. So where's 1? 1 is here, and from the right, it needs to go down to infinity, negative infinity. That looks great. From the right, oh no, not here. This is from the left. That's from the left. It's not B. From the right, it needs to be going to infinity, negative infinity. So that's one's okay. Oh, no. From the right, no, this is from the left. So we're talking either A or C. All right. It looks like the limit as x goes to 3, no matter which side you're on. That thing's going up to infinity. So as I get close to 3, there should be a vertical asymptote. And on each side of that line, I should be going straight up. A is looking great. Oh, C is not. At 3, on the left, you're going to infinity. On the right, you are not. The answer is A, straight up. Oh, here's 18. Sketch a possible graph of a function f together with vertical asymptotes that satisfies all the following conditions. F of 1 is 0. Looks like it hits the x-axis at 1. Does that disqualify any of these yet? Nope. They all hit the x-axis at 1. F of 3 is undefined. Okay, so some bad stuff happening at 3. That's all true for each one of these. Okay. The limit as x goes to 5 of f of x is 1. All right, so at 5, it should be 1 unit above. So 1, 2, 3, 4, 5 looks good. They all seem to do, uh-oh. 1, 2, 3, 4, 5. This is not 1, right? Oh, this one's out too. 1, 2, 3, 4, 5. This is not the number 1. This one's out. All right. The limit as x goes to -1 from the right of f of x equals -8, negative infinity. This means on the on the right of -1, this thing needs to be going down, 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 down. Let's find -1. At -1, it needs, on the right, it needs to be going down, and look at it. It's going up to the right. And we can verify all this other stuff, right? On the right of -1, here's -1 right here. On the right of -1, it's going down, and I'm sure we can verify everything else. As you go to 3, here's 3 on both sides. You're going to infinity. And for 7, on the left of 7, you're going up to infinity as well. Straight up B. Do a few more. Sketch a possible graph of a function g together with the vertical asymptotes satisfying all the following conditions. This needs to go through the point 3, 1, and it needs to go through the point 9, -1, and there's a vertical asymptote at 8, and it better be going to negative infinity. So around 8, this thing better be bottoming out. Oh. 1, 2, 3, 4, 5, 6, 7, 8. Should be going to negative infinity at 8. I don't think that's happening at A. Should be going to negative infinity at 8. This one's not doing the same thing either. And the reason is because look at 8. Look, there should not be this going up around 8. Right? Around 8, you need to be going down, 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 down. Right? This looks better. So we're talking about C or D. Let's look at some other information. As you go to 10 from the left, it needs to be going up, 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 up. 10 from the left. Where's 10? 10 is here. From the left, looks like you are going up, up, up. 10 from the left, looks like you are going up, up, up. Okay, that's good. 10 from the right, you need to be going down. 10 from the right, you need to be going down. C's been eliminated. D's the winner. 10 from the right, you need to be going down. All we're doing is translating, family. As you'll see from these off the record, that you only need to look at a few of them before stuff just starts to get eliminated. This needs to go through the point 4, 1. It also needs to go through the point 7, -1. Let's deal with this in terms of asymptotes. As I go to 5, I need to be going all the way down to negative infinity on either side. As x goes to 5, on both sides, I need to be going down, down, down. Okay, that one's okay. As x goes to 5, I need to be going down, down, down on both sides. Great. Uh-oh. As x goes to 5, I'm going down on this side and up on this side. It's not that one. As you might expect, this one's going to be eliminated too. Down on the left, up on the right, and I need to be going down on both sides. 10 is going to decide this whole thing. On the left of 10, I need to be going up. Looks good. On the right of 10, I need to be going down. On the left of 10 going up. On the right of 10 going down. B wins. #21. So now we're going to have some functions that have some vertical asymptotes. So what we want to do is we know that if I ask about 1 over x minus 9 and I plug in 9, I'm going to get some bad stuff. Now, all we're doing in this case right now is trying to mathematize what we feel like bad stuff is. And what bad stuff is in terms of real numbers here is that we're not going to get a real number, but we are going to get this concept of infinity or negative infinity. And so when you're dividing by something really, really small, it makes the entire fraction really big. And so all of these answers are either infinity or negative infinity, right? The first two. And then we'll deal with the last one in a second. But the way that you check whether it's positive infinity or negative infinity is you just need to check a value to see what the sign is. So as I go from values of x to the right of 9, those are values of x bigger than 9. And if I'm plugging values of x bigger than 9 into the function, well, let's take an example, 9.1. That would be one of the values I would check for the limit if I was taking the limit from the right, values of x bigger than 9. If I plug this in, I just need to check the sign. 1 over 9.1 minus 9 is 1 over 0.1. That's 10. I don't really care. I know it's positive. It's positive infinity. I don't even need to put the positive sign there, just infinity. Similarly, but the opposite, if I put in a number like 8.9, I know that 8.9 minus 9, and by the way, I'm putting in 8.9 because I'm coming from the left of 9. I'm coming from values of x less than 9. When I put in 8.9, 8.9 minus 9 is negative 0.1. If I looked at this thing, it would be negative 10, and it would only get worse the closer I get to 9 on the left, negative infinity. The limit from the right is positive infinity. The limit from the left is negative infinity. The limit doesn't exist, and it's neither infinity or negative infinity. The limits need to be the same in order for me to conclude that. Same game here. I'm going to pick values of x, and all I'm doing here is checking the sign. Values of x that are bigger than 3, 3.1. 3.1 minus 3 is 0.1. Negative 4 over 0.1 to the fifth is negative. From the left, if I put in negative 4 over, and I put in the number 2.9, 2.9 minus 3 is negative 0.1. Negative 0.1 to the fifth, I can calculate this, but a negative number to the fifth power stays negative. The numerator is negative. The whole thing is positive, positive infinity. Oh my goodness. The limit from the right is negative infinity. The limit from the left is positive infinity. The limit itself does not exist and is neither infinity or negative infinity. We're going to talk about vertical asymptotes. So vertical asymptotes are the things that make the denominator 0 that you can't cancel. So this is going to be a question of just factoring. So we'll factor the numerator, factors of 18 that add up to negative 9, negative 7, negative 2. Factors of 6 that add up to negative 5, negative 3, negative 2. And now alarm bells are going off because we know now that 3 and 2 are serious problems, but only one of these is a vertical asymptote, right? 2 is not a vertical asymptote because I can just go ahead and cancel out the x minus 2 so that 2 does not present us with the problem of dividing by 0 because it gets canceled out. 2 would give a whole, and then 3 is the one that makes the denominator 0, and that would give us a vertical asymptote. And so when we cancel, we get something like x minus 7 over x minus 3, and now we can check this. The vertical asymptote is x equals, let's see how they want us to answer. So it's x equals 3. The limits of this vertical asymptote, oh, let's see. Now we have to check to see if the limit exists. So the difference between A and B is that one says that the limit does not exist and one says that the limit does exist right here. Okay, great. So let's take a look. So now we've got x minus 3, x minus 7 over x minus 3. So now the question is, we need some space. Let's get some space down here. X minus 7 over x minus 3. And the question is the limit as x goes to 3 from the right, that's either going to be infinity or minus infinity. And the limit as x goes to 3 from the left, that's either going to be infinity or minus infinity. And if they're the same, then we're going to pick A. If they're different, then we're picking B. All right, we know the plan. The plan is to pick a value like 3.1 and check the sign. 3.1 minus 7 over 3.1 minus 3. 3.1 minus 7 is a negative over 3.1 minus 3 is 0.1, which is a positive. The limit is negative infinity, a negative over a positive. Here we're going to plug in a number less than 3, 2.9. 2.9 minus 7 over 2.9 minus 3. Looks like we're picking B, family. 2.9 minus 7 is a negative over a 2.9 minus 3 is also a negative 0.1. A negative over a negative is a positive. This limit is positive infinity. The limit from the right is is negative infinity. The limit from the left is positive infinity, and there is no limit. And it's neither infinity or negative infinity. So there's a vertical asymptote. So the answer is B. There's a vertical asymptote at 3. The limit from the right is negative infinity. The limit from the left is positive infinity. And the limit does not exist because these two things are not both the same infinities. We'll talk about this in class. Infinite limits, that the limit as x tends to infinity of 1 over a power of x, as x gets larger and larger and larger and larger, the fraction itself, 1 over that, gets really, really small. This is 0. And it doesn't matter whether I put 10 over it or not. The denominator is going to get much, much bigger than the numerator. This is going to be equal to 5 plus 0, which is 5. This goes to 0. So that first one was an example where the power in the denominator is higher than the power in the numerator. Here the powers are equal. And when the powers are equal, you just take the ratio, the coefficients of the highest powers. So the coefficient, when the powers are the same, the coefficient of 3x squared is 3. The coefficient of this x squared is 1. The answer is 3 over 1 when the powers are the same. We need to know the end behavior of e to the minus x. So e to the minus x or e to the minus 8x looks like this. All right, so this is one that we need to know. As x goes to infinity, that's this way. So that means x is going to get larger and larger and larger and larger. What happens to the graph? It goes down to the x-axis, which is 0. So all the way to the right, the positive infinity, it should go to 0. To positive infinity, it should go to 0. And what happens when it moves all the way to the left? Goes to minus infinity. Looks like the function is going all the way up. That's A, right? So there's nothing to do there, just familiarity with the exponential function. Again, as we said before, calculus is going to be about using these functions we learned in pre-calculus to answer some problems. 27. Here we're going to find some horizontal asymptotes. Again, we said that let's look at the ratio of the powers. When the powers are the same, you just take the ratio of the coefficients, 8 over 2, which is 4. For the same reason, because the powers are even, as you go the other way, it's still 4. 8 over 2. The horizontal asymptote is the line y equals 4. Determine the end behavior. Again, just learning about e to the x. So e to the x does this. But now I got a big old minus sign in front of it, right? So this is e to the x. So minus e to the x flips it over the x-axis. So minus 2e to the x flips it over the x-axis. So now, as I move all the way to the right on this graph, I'm asking what's the limit as x goes to infinity. As you go this way, this graph flies down to negative infinity. And as you move all the way to the right, ooh, we'll use green. As you move all the way to the right, it looks like the graph goes up to the line y equals 0, which is 0. Which graph is that? That is this one. $29. We're going to do some horizontal asymptotes. We're just looking at the highest powers. The highest power here is 2. When you do this x times this x, that highest power is 2. So the highest power in the numerator is 2. The highest power in the denominator is 2. So the powers are the same. The coefficient of the numerator is 1. The coefficient of the highest power in the denominator is also 1. The horizontal asymptotes are y equals 1, or in other words, the limits as you go to the infinities are both 1. The horizontal asymptote is y equals 1. Vertical asymptotes means you need to set the denominator equal to 0 and solve. So again, we're going to have this, it's x squared minus 4 over x times x minus 2. The first thing we got to do is fully factor. And when we do that, we see that we're going to cancel. And so upon initial inspection, it looks like we have issues when x is 0 and when x is 2, because those are the values that make the denominator 0. Again, just by setting the denominator equal to 0 and solving, we know that at least we're going to have some holes or vertical asymptotes at 0 or 2. We do the business of canceling. Cancel this, cancel that. X plus 2 over x, and now we still have a problem at 0. And the question is that problem going to give me a limit that's either infinity on both sides, negative infinity on both sides, or maybe infinity on one side and minus infinity on the other? We need to take the limit as x tends to 0 from the right of x plus 2 over x, and then we'll look at the limit as x tends to 0 from the left of x plus 2 over x. One of these is infinity, one of these is minus infinity. Let's see. So here what we're going to do is we're going to pick a number slightly bigger than 0. Let's do 0.1. So 0.1 plus 2 over 0.1 is 2.1 over 0.1. It doesn't matter what that number is. We know it's positive. From the left, I'm sorry, from the right, it's positive infinity. If we plug in negative 0.1, then we get negative 0.1 plus 2 over negative 0.1. That's 1.9 over negative 0.1. That's minus infinity. The limit on the right is plus infinity. The limit on the left is minus infinity. Looks like we're talking about which one? Looks like it's A. There's only one place where you have a vertical asymptote. We named it. It's 0. The limit from the left was minus infinity, and the limit from the right was positive infinity. B would be if you had more than one answer for a vertical asymptote, but we only had one because the 2's canceled. All right, family. Hope it helped. See you in class soon.